Very good morning to everyone. As part of this product development cycle, now we are entering into day two. Day two, I am immediately, as suddenly I took interrupts. Yes, in the last session, I just explained you how to toggle a LED in a motherboard. But now immediately before expanding other small stuff, addition of two numbers and other things, I immediately jump to interrupts. Why? The reason behind that is when you start developing automotive ECU, for either the small examples that we have, no, that is covered by others. There are many lot of codes available in the internet, and even YouTube videos are available. And even for interrupts, theoretically, there are a lot of materials available in the internet. When it comes to practical, there are very few. Again, these interrupts are very much needed when it comes to automotive issue, because as we know that embedded system is not a time bound one, so there will be an infinite. It won't be terminated at some point of time. It will be continuously running in its entire life cycle right now. So there will be a task in automotive ECU that will be performed always. There is such one activity which is performed always, and another activity which is like a small period of time that task will be executed, and then the program control or microcontroller control will come back to the original service. So there will be different tasks to be done when there is a need. Once that is completed, the ECU will come back to its normal activity. Otherwise, the set of tasks that it used to do always, right now, probably acquiring the samples from sensors, those sort of things, right now. These tasks, those are performed always now. So they will be in the in a infinite loop. So it will be in an infinite loop. The ECU used to do that always, right? When a particular task to be done, when we want to do a specific task which is not our usual task, then we have to switch our program counter or program control from the usual task to that subtask, and we have to complete the task and come back to our original task. Let me give you an layman example. Right now, you are you have a home and you are doing some day-to-day activities. For example, in the morning you wake up and then you bath and then you pray, and then you start studying your subjects that you want to, and you are seeing the news. These are your routines that you used to do in a everyday life. Right now, it has everything. You have a schedule for that. Okay, I will wake up in 4:30, and then I bath by 5, and then I pray by 5:30, something like that. After praying, I go out for walking up to 7. After walking or exercises at 7, I will come back to home. I will watch the news and read newspaper up to 8. From 8, I will have my breakfast. Then by 9, I will go to office. This is your normal routine. While you are doing this normal routine, okay, you are studying, you are reading your newspaper. In that time, your water tank that you have in your home, right, that overflows. What you will do? Will you continue reading newspaper, or you will suspend your current operation and will go and solve that problem? Because that is higher priority. If you leave that as such, your entire home will be flooded, and sometimes if you run it for a long period of time, electric motor may fail, So these are the different result that we will achieve if we don't react to that situation. So this is called as interrupts. So the interrupts means you are doing a normal activity which has a schedule. Right now, while doing it, you get an interruption. Right. Yeah, tank overflows. A stranger knock your door. The cat, your cat, it pushes the milk vessels or something like that. These are the unexpected thing or a task that for that we need a reaction. If we don't react to that action, that is our, we may get a wrong result or we may get a issue. So the interrupts are like a special task. They will be they should be serviced when requested, right? No, so when the interrupts occur, that program control will be transferred to that interrupt function and it will execute that function. The number of program lines executed when a particular interrupt occurs, no, that is called as interrupt service routine. We have seen two things. The interrupts means the interruption that happens in your day-to-day activity or your usual schedule, right now, which makes you to suspend your current operation and go to service another task, right? So that is called as interrupts. The routines, that is number of programming line that you execute, no, when a particular interrupt occurs, that is called as interrupt service routine. This is very needed in automotive industry because upon receiving a CAN packet, you may do some things. Right now, upon changing a signal, you may do something. When a particular signal is changed in the CAN bus, you may have to execute some piece of code. These are very common in automotive industry. So we should know if that is the case, if the automotive ECU is going to respond to these different interrupts, and it will also have its own schedule to execute. In this thing, when we come to know these things, we have to know how to program them, program the interrupts in an automotive ECU, how to work with that. Those who studied 8051 or this microcontroller subject in their engineering, they can understand the interrupts to some extent. Those who are from mechanical background or mechatronics background, for them, it may be a little bit, what I say, it may be a little bit hard to understand, but it is very easy. As if you relate the example that I told, the layman example that I told, you can understand what interrupt is. Right now. Okay, why we need that one? As I told you before, the automotive ECU need to execute some piece of code when certain event happens upon receiving a CAN message, upon changing a signal, right? Upon a failure. Like that, we need to react. We have to suspend our current action and have to go to service and another function, right? That is very common in automotive ECUs. That's why we have to understand about interrupts, right? What is the difference between polling and interrupts? There are two things available when it comes to executing in another service or executing a task. There are two things, like one is polling, another one is interrupts. What is the difference between these two? The polling will not have a separate task programmed separately somewhere as we do for interrupts. It is not a separate function. The polling is like you are continuously monitoring certain event, continuously monitoring certain event. When that event happens, you will react to that. The interrupt is not like that. See, in your natural flow of program, it's actually, you all know that the C program execute from the main, because the main is a starting point of the C program. After executing the number of steps that we have in the main, we used to have a infinite loop In that loop, we used to continuously monitor events. If that event happens, we used to check whether that event happens, whether that event happens, whether that event happens. If that event happens, we will go and do certain action. So there is no context switching. There is no program control transfer to one from main to some other service. No, not like that. It is just like a continuous top-down flow of your embedded C program. So in that, you will continuously monitor that one. Let me relate this to a real-time example. You have as you have a normal schedule. In that normal schedule, that is, as I told you, you wake up in 4:30 and then bath by 5, praying by 5:30, going walk by 7 and return by 8. So this is your normal routine. In this routine, when you are doing this routine, see, when you are doing this routine, you will go and check whether I turn on the whether there is a overflow in the water, whether there is a cat inside my home, whether there is anyone knocking my door. So I used to go, if I do like that, no one will do like that, I'm saying. So if I do all these things when I doing my normal activity, that is called as polling. What is the overhead when we enter into polling? When we enter into the polling, we are consuming plenty number of machine cycles to check them. Though that may happen, may not happen. The probability it can happen, it cannot happen. The cat can come inside your home and push your milk, or it can do it, or it cannot happen also. So somebody can knock your door, or they cannot knock your door. They don't knock your door. So these are the we have a that is like it can happen or not happen. Like that, we have a probability. But what polling used to do, whether that happens or don't happen, it used to go and check whether that happened or not. If it is no, it will do that. It will go and check for the next activity. So this is called as polling. The polling has an overhead of more number of machine cycles are consumed. So it is not a perfect way of doing perfect. It is not a perfect way of writing program. That's why the interrupt comes. The interrupts are very great implementation in a microcontroller that helps us to do that helps us to simplify our machine cycle and achieve what we want. But pooling as well as interrupts, both of them have their own advantages and disadvantages. When it comes to interrupts, you cannot simply jump from your current programming, executing current current execution to some other service and execute that and come back like that. You cannot do like that. You have to push your current program counter value to stack, and then you have to push all your intermediary value that you are having in your main program to the stack memory before you go to that task, because if you simply leave them and go to service another things when you come back, so you need those data, right? No, those intermediaries values are needed for you. So we cannot do something like, even when we use interrupts, we cannot simply jump from here to there and do the things and then come back here. No, we have to do some sort of pre planning. Like before we switch to another service, we have to push the necessary, we have to store the necessary intermediary variables, program counters in the stack, and then we have to go to that service and service that service. After doing that service, we have to pop values that we pushed it to stack memory to again respective registers. Then we have to proceed. So this is, you need a little bit strong programming knowledge to use interrupts. The polling is not like that, because there is no switching of task, and you will write. There won't be, you no need to take any backups in the polling, because it is a continuous program executions. So that is the advantage that we have in the polling. It is not it is a limitation. Everybody has their own limitations. interest has its own advantage and it also have its own disadvantage. The polling has its own advantage and disadvantage. So it is the decision of architect of the ECU product who has to decide which one is suitable to me, whether I can go for polling or I can go for interrupts. So that choice he should make, right? Then how interrupts are better than polling? That is I explained, right? It's because polling consumes more number of mission cycles to check different things. It is not like interrupts. So because of that, we have a overhead of more machine cycles in polling. That's why uh, the interrupts are very far better in that thing. So it is a separate task written somewhere, and you will switch. You will do a continuous normal activity that you usually do when you need to service that one. You just push all your intermediary variable to stack and jump to the service that's do that service, and then come back to main, pop all those things and continue your job. So like that it is. Different methods of implementation of interrupt service routines in microcontroller. So there are in the modern or the microcontrollers available in the market today, no, they are some of the microcontrollers comes along with interrupt vector table. That means every event for which you need a service, no, so they used to number them like okay, this is uh, uh, for timer interrupts, the address is vector address is 04. And then there is another address 06 is for serial port interrupts. Okay, another interrupts vector. So they used to provide you a table. If that particular event happened, that is program counter will be loaded to that program address. Actually, the vector table is nothing but the vector that is program memory addresses. In those addresses, we used to give these addresses to the functions or the service routine that we want to do. We used to have a branch or a transfer of control from that memory location to the whatever the service that we want. That is configurable right now. So this is called as the product with IVT. That means product with interrupt vector table. There are other microcontrollers, those they don't have any defined interrupt vector table. They don't have any vector table. So in but when there is a interrupts, they can switch to the memory location. One fixed service, interrupt service. In that you can have a different divisions. Like when a particular, if this interrupt happens, what it is to be done, like that. So these sort of microcontrollers are called the microcontrollers with no IVT, right now. So we are going to discuss in this session with a microcontroller which does not have a IVT of its own, right now. That is the thing. Different method of implementing interrupt service into microcontroller. That's what I told, no, IVT method and the non-IVT method. Finally, why we need it for embedded ECU? Why we need interrupts in the embedded ECU? I believe that I covered that one. I think why we need it. Here we covered it, no? So I believe this is a repetition. Let me remove that. So maybe we can add an additional point. How to implement the interrupt service routine using in embedded C? There are every compilers has their own ways to implement interrupts right now. So there is no, in embedded C, there is no keyword called interrupts. No, not like that. It is not in the NCC. We don't have such thing. So every compilers have their own way of doing interrupts. So you have to see the user guide or user guide from the particular developer guide from a particular microcontroller supplier to understand how to implement interrupt service routine for your, because there is no keyword called interrupts in ANSI C or even embedded C, that we have to understand. So these are like compiler specific. So whoever write the compiler, no, they have their own style of writing things, writing interrupts, right? No. And then in front of us, in my lecture, always I use an example, and then I will try to implement that in front of the students so that they will get a clear idea about what I am trying to say practically. So now our aim is, here is a problem statement: implement ISR to toggle LED in the motherboard. ISR means interrupt service routine. To toggle the LED in the motherboard using PIC 16F887 and embedded C. So we are going to use PIC controller as an hardware. In that embedded C, we are going to write an embedded C program and flash it. That's how it is. This is my second day research as which is needed for our embedded product. I made a research on that one day complete research, and then finally I tried to implement that in embedded C. I got the success. So now we are going to demonstrate that how we have implemented that, and also we are going to explain in the program. Okay, now let me bring the data sheet now. Sorry, let me bring the programming environment first. So here is a project that we are using, and then I just use it's a main version 0.2. We can change that into, we can rename that. Let me check whether that is possible. Yes, it is possible. So I want to call that as ISR main version 0.2. Otherwise, we can have main in that, but the main which speaks about ISR, right? So right. This is the code that we have here. But in this code, I have initially the very first step that we have to do in every controller is setting the configuration registers. That is the thing that we have to do. So we all know what are the necessary settings, like creating an external clock out. That means oscillator, using an oscillator, external oscillator for clocking, and then disabling watchdog timer. Right now that is turned off because we no need at this point, because our program is not such a big right now. So because of that we turned it off. We have other things like power up timer enable bit like that. So those things that we don't know now, so that we just set it off, and brown out reset selection bit, internal external switchover bit. So these are the different things that we have. This configuration, this pragmas, right now preprocessor directives, you can generate them by configuring that in your GUI. Right now, before you do this configuration, you ensure that your device is, you have selected proper device. If your device is not proper and you are doing it, it will be a little bit, so you can do a wrong settings for your control registers. So how to select the proper device, that you can do it via properties. Right click on properties, projects, and then come to properties. In properties, we have something called as here like device. You can pick the device that you are using, and also have to pick the necessary compiler tool chain. So these are the settings that we have to do before we go for configuration setting. Then we have something in production, set configuration bit option. This is a GUI. In this GUI, you can configure your bits that you want graphically. Right now, I have drop downs here. Whatever that we want, I can configure this. After doing it, hit this generate source code to output. So when you do so, you will get these sort of lines, pragma lines. So just copy them and paste it here. they provide that, that this is inbuilt option that we have in MPLAB IDE. Then I included a header file. Then I have written an interrupts. This is MPLAB C compiler supported keyword __ interrupt. So don't think that this will be same for other compilers as well. Compilers of Texas or analog devices like that. So every manufacturer has their own way of implementing their interrupts. You have to follow their user guide. As per the MPLAB user guide, you can get this point in their documentation. So interrupts, and then you have to declare that function as void. Inside my service routine, what I am checking, PIR1 bits. That means there is a register in this controller called PIR1. In that, we have a, what is it, bit. That bit is called as TMR, timer 1 interrupt flag. So I am checking here, when I enter into this interrupt service routine, I am checking whether that particular flag bit is set. When that will set, if there is a timer overflow. If there is a timer overflow, only then PIR1 register will be, that is the timer 1 interrupt flag will be set in PIR1 register, because it is part of that register. If it is so, what I do, I simply toggle port D bits. It's from current value to, that means I toggle it if it is 1, I make it 0. If it is 0, I make it 1, which means I am simply toggling. And then PIR1 bits. And in that PIR1 register, I clear timer 1 interrupt flag, because it is mandatory. After you service the routine, and the end of your service routine will be clearing the flag that user routine should do. That's why I clear that flag, and then I come out from that interrupt service routine here. I have written that interrupt service routine as a function right now. After that, we have main function here. In the main function, initially I disable all interrupts, because we are going to do some settings, and so that we don't want to immediately, that is program control should not switch to any interrupt service routine. That's why we disable all interrupts globally. After that, I enable timer 1 interrupts is enabled, and then timer 1 interrupt flag is cleared, because these two things we have to do, because I am going to use timer 1. Right. After that, I have set timer 1 control register. The timer 1 control register, no, in that what I am doing, I set the prescale value. Because number of the oscillator value divided by 4 will be given to maybe 5 megahertz will be given to the timer. So that is very huge clock. So that I am dividing it by configuring the prescale value as 3. If I do so, further that 5 megahertz divided by 8 will be supplied to the timer, so that we can have more delay. So that is the aim goal. After that, I clear the TRISD bits to 0. That we all know, when we said that when we use TRISD, we are using all our port D bits, port D pins as output pins. So we are going to give output through them. After that, I have a FDE8. This is just like some what is it, 430 millisecond, I believe. That much of delay we want to create in between interrupts. So for that, this is the word. As I already explained the calculation in the first video, I use the same to achieve this. Maybe I may included the prescale value as 3 in that formula, so that I got this word. Right. After doing it, after configuring timer H and timer low, then I go for interrupt. I enable peripheral interrupts, because all peripherals need a clock. Without clock, they will not work. So I enable peripheral interrupts right now. Sorry, I'm not enabling peripheral clock. I am enabling peripheral interrupts, because this is a global flag that we have to set when we want the peripherals to create interrupts, the timer interrupts or ADC interrupts, serial port interrupts. In order to in order to create interrupts by those peripherals, we need to set this bit. So it's controlled. It is like a centralized control of all peripheral interrupts. So I set that bit to 1. Because of that, I enable. Because of that, that particular interrupts is enabled, which will also enable the timer on interrupts right now. So then global interrupt enable. This is a global interrupt enable is like whether it is a processor generator interrupts or a peripheral generator interrupts, it doesn't matter. So it will control everything. So maybe you can say peripherals as a state and global as a central, so that the central has more power than state, so they can have control the states. No, in that way we are having this peripheral interrupt enable bit we set, and then we also set the global interrupt. Moment after doing it, I turn on the timer. So the timer will be started, and then I just wait in while loop. So as my there is no block here, so it will simply wait here, continuous, otherwise infinite loop. So it used to wait here. When there is a overflow, it will generate the interrupts. When the interrupt have occurred, automatically, because they will generate the necessary code for that when you compile it. So it will come here. The program control will push all the things to stack memory, and then it come here, and it execute this service. So it used to in this service routine, we check whether the timer interrupt, that means timer overflow happens. If that is the case, we toggle the pin, and then we clear that flag bit. Right now, when we do that, the service is over, we will return. When we return, where to return? We will return to the loop, because that is the very last point that we are doing. So they will come and wait here. So if there is an event, they will go and service it and come back. If there is another event, they will go and service and come back. This used to be, this is how the ECUs, automotive ECUs used to be. So for that only, I have implemented this one. So let me compile it. Now I am going to flash. So for that, I have to connect my controller here. Then I read my controller, right? After that, I import X file. And then after selecting that, I just write it. Done. So I can, now I am removing the controller from the flasher, and I connect that to my board, motherboard. After connecting, oh, sorry. After connecting my controller to motherboard, I turn on the power. So it's toggling in my board. It is toggling. It's doing the job. Okay, it's doing. So okay, team. That's all for today. Our day 2 goal is achieved. let me come back to you with another detail. Tomorrow, we can explore our next step towards our product development. If you have any comments in this thing, or you have a doubt on certain things, uh, comment comment in this video. Also share this video to your the people who are interested in these sort of topics. Thank you for watching.